everyone and welcome back to Physics Unlocked. I hope you all are doing well. Today we are diving into part 3 of our Scalars and Vector lecture series, where we will explore the rectangular component method for adding vectors. So let's get started. Okay, so to understand the addition of vectors using rectangular component method, let's start with a simple scenario involving two vectors. Consider vector A1, which forms an angle theta1 with the positive x-axis, and vector A2, which also forms the angle theta2 with the same x-axis. Now let's proceed to add vectors A1 and A2 using the rectangular component method. As a prerequisite, recall the part 2 of this series, how we resolve vector into their components. Building on that foundation, we will apply this concept to add A1 and A2. So first of all, to add A1 and A2, we will draw an x-axis and y-axis. So O point is representing the origin, right? So this is vector A1, this is vector A1, which is making angle theta1 with the x-axis. Now what I will do, I will use the concept of head to tail rule and I'll draw this vector A2 on the head, or you can say the head of the vector A1. So this is vector A2 over the head of the vector A1, and I've drawn a simplest reference axis over here, which shows it makes an angle theta2 with the x-axis, and I've given name this point as A and this point is B. Now what I'm going to do, I will add these two vectors A1 and A2 by using the concept of head to tail rule, and I'll draw a resultant. How we draw a resultant? This resultant is drawn in such a way that it joins the tail of the first vector to the head of the second vector, right? And this is the resultant, which is the sum of the vector A1 and A2. This is the thing which we have already started in the previous lecture, right? Now what I am going to do, I will resolve A1 vector into its component. And how we are going to do that? We will draw a line over here on the x-axis and a line here on the y-axis, and when you add these two components you will get the vector A. So this is the component A1x because it's a x component of vector A1, and this is the A1y. So you can see by the head to tail rule, you can see here when I add A1x vector into A1y, then this is the resultant, which is A1. So these are the two components, the x component and the y components, which are known as the rectangular components of this vector A1. Now I will do the same thing with the vector A2. Look at here. So this is vector A2x on the x-axis, and this is vector A2y on the y-axis. So when you add A2x into A2y by head to tail rule, then A2 is representing the resultant of this A2x and A2y. And these A2x and A2y are known as the rectangular components of the vector A2, right? And this point is, let's say, C point. And now what I'm going to do, basically, I will draw all A1x and A2x, both the components on the x-axis and both the y components on one particular y-axis. Why I'm going to do that, I'll explain it later, but look at here. If I wanted to move this A2x over here, so I will use the concept of a free vector. Now what is free vector? Free vector is a vector which can be displaced parallel to itself without changing the magnitude and the direction of the vector. So you can say the magnitude and the direction is same, so I can give it name as A2x. Now you can see both the components of x, both the x components of both vectors A1 and A2 are on a single axis now, x-axis. Now I'm going to do the same thing with the y because a2y is over here, but there is no a1y here. So I will use the same concept of free vector, that I can move this a1y over here. So I can displace a1y parallel to itself without altering its direction and magnitude. Okay, so you can see that a1y and a2y are now on a particular line, and we called it as a y-axis. And if I write that, and this point is D, let's say, and this point is E, let's say. If I recall the points, this is O, A, B, C, D, E, right? And if I write the equation for the x-axis only, so the resultant of the x-axis is the sum of the a1x and a2x, right? And if I write the resultant for the y-axis, then it's the sum of a1y and a2y. And you can see the amazing thing that when you add Rx into Ry, then you will get the resultant R. So what we have done, we have added vector a1 and a2 into by the help of rectangular component method. Now we are going to write the equations for this. So we are going to write the equations for a1x, a1y, and a2x and a2y, means for the rectangular components. Okay. So first what we have done, we have resolved the vector a1 into its rectangular components, which are a1x and a1y. So how we are going to write the magnitudes of these components? You have studied this thing in the resolution of vector, that for x component we use cos theta, and for y component we use sin theta. So if I'm going to write the vector for vector a1x, so the magnitude of vector a1 cos theta 1. Theta 1 is the angle which is a1 is making with the positive x-axis. And for y, we will write the same equation, but cos is replaced with the sine. Now, if I write this equation for a2, then you people tell me that what will be the equations. Just take a minute and recall the equation. Okay, so the equation will be a2x is equivalent to a2 cos theta 2, right? And a2y is equivalent to a2 sine theta 2. Clear? Now we are going to write the equation for the x components, the resultant of the x and the resultant of the y. Okay, so the resultant vector along x-axis can be determined as, you can see it's this x-axis, the resultant of x is the sum of the two quantities, that is a1x and a2x. So how I'm going to write it? OD is equivalent to OC plus CD. And if I substitute the value, so OD is representing the overall resultant, that is resultant X, and OC is representing the A1X component, and CD is representing the A2X. And if I substitute the value from the previous equation, that A1X is equivalent to A1 cos theta 1 and A2X is equivalent to A2 cos theta 2. And if I write this equation is in the magnitude form, right? If I write this equation in a vector form, then the Rx, we will put an arrowhead on the Rx, but this is the magnitude and we use the unit vector to represent the direction. So for x component, the unit vector is I cap, and this is also the x component, so unit vector is I cap, right? The same thing we will do for the y-axis, resultant vector along y-axis. So you can see it is equivalent to D plus DB is equivalent to DE plus EB. Look at here. The overall is DB, that is equivalent to DE plus EB. And you can see the total DB is the resultant y, which is the sum of A1y plus A2y. And if I substitute the value, A1y is A1 sine theta 1 and A2y is A2 sine theta 2. This is the equation that is written in a magnitude form. If I write this equation in a vector form, then I need to add a unit vector here. So the unit vector that is along y-axis, it's j cap and j cap. And to write here, I will put in arrowhead over here, right? Okay, so the final resultant vector. Now we are going to find the magnitude of the resultant vector because we are done with the Rx and Ry. Now we will find the R. And how we are going to find the R? Because you can see it's a right angle triangle, right? Rx will be added in Ry, then it's R, and it's a right angle triangle. And to find this side of the right angle triangle, which is the hypotenuse, then we use the Pythagoras theorem. So using Pythagoras theorem on a triangle OBD, then hypotenuse square is equivalent to base square plus perpendicular square. So what is hypotenuse here? It's R square. And what is base? It's Rx square. And what is perpendicular? It's Ry square, right? And if I wanted to find the value of R, then taking root on both sides, then this will be the equation. And in the previous slide, we have seen the formula of Rx and Ry. Just substitute the value of Rx and Ry. You will get the magnitude of the resultant vector, right? Now, if I wanted to find the direction of this resultant vector, which is represented by this theta, and this theta is the angle that is made by the resultant vector with the x-axis, then you know that to find the direction, we usually use the concept of the trigonometry of tan theta. And tan theta is equivalent to perpendicular over base. And from figure, you can see the perpendicular is Ry and the base is Rx. So when you substitute the value of Ry and Rx, you can find out the theta. And what is theta? Theta is the angle that the resultant vector makes with the positive x-axis. That's all for today. Thank you for tuning in to the Physics Unlocked. If you enjoy this video, please consider subscribing to my channel for more engaging physics content. Your support means a lot. Don't forget to hit the like button, share your thoughts in the comments, and spread the knowledge by sharing this video with your friends and family.